Okay, the last item for today is there are a couple of things that are worth paying attention to for the future of your career. First off, psychology uses an awful lot of measures that infer the underlying construct because we can't directly see the things that we want to measure, like how depressed you are. So we have for decades had what I can call Stone Age test theory. An example of that is you get a sample of depressed people, a sample of non-depressed people. You form 50 items and then you give them to both groups and look for those items that the two groups endorse differently. Out of them, maybe you choose the best 20 items that the depressed and the healthy endorse differently. Now, in the future, we'll give all 20 items to people who come into our clinic, and we assume the more items they endorse, the more likely it is that they're depressed. So during test development, here are the assumptions we're making. All depressed people are identical. When we're separating out which items discriminate depressed from normal, we don't account for differences in depression. The depressed are depressed alike. Ditto for the normal. They're as self-similar as eggs in a box. All differences in how patients endorse items we assume are due to the content of the items. Then when we move the test into clinical use, we assume that all items are identical. Each item is just worth 1 point. And all people are in one group, patients walking into our clinic. The number of points says how depressed they are. So notice that on the left-hand side, when we're developing the test, we have 50 items which we can rank order from most effective to least effective with very fine distinctions between items. This one is better than that one in the second or third decimal place. But then when we go to the clinic, the items we force to be identical, and now we can discriminate people to 1 part in 20 because we have 20 items and a 19 is a little higher than an 18. This problem is called a nexus. When we're doing test development, we don't have a way to account for different people react to different wording differently. So some of the variance between items is actually due to differences amongst people in the depressed group or in the normal control group, and vice versa. We don't have a way for accounting for variability on both sides of the problem at the same time. Stone Age. Okay, Iron Age test theory is the rash model. You will see the rash model or rash analysis in article titles, so it's important to know what this is. We have an underlying continuum of depression. It just runs from low to high here. And we have no yes items. Let's assume that they're all set up so that if you say yes, you're more depressed. Okay, take item number 1. As we go from low to high, there's a point along the scale where people flip from saying no to saying yes. But then for item number 2, there's going to be a different point at which they flip from no to yes. And for item number 3, there's yet another point where people are going to flip from no to yes. If we have enough subjects, like 20 subjects per item, we can recover those points from the responses that people give to the items, and we can construct a much more fine-grained estimate of exactly where you lie on this depression continuum based on which items you endorsed. That's the rash model. Space age test theory is item response theory. Rather than assuming there's a point at which people flip from no to yes, we look at the odds that people are going to respond no versus yes as you go from low to high on depression. So there's a point of 50% likelihood of saying no versus yes, and at that point we have a slope. But then item 2 has a different point of 50% likelihood and a steeper slope. And item 3 similarly. Okay, that's full item response theory, and those patterns can be recovered from the data. This is an article published in 1999 where the author used item response theory thinking to examine the stages of change. So I assume that you're all familiar with pre-contemplation, contemplation, action, and maintenance as people move through recovering from substance abuse. Well, the author's thinking was, if this is truly a stage model, then I should be able to find items where as you move through the stages, you will reach a point where you flip from saying no to saying yes, but then you'll reach a later point where you return to saying no because you've left that stage. And another item should have different points at which you switch to endorsing it and then switch away from endorsing it again, and a third item, and so on. So this author developed a number of items to examine where you are in the process of change regarding smoking cessation, and was able to recover 10 stages of change. This is the kind of finer-grained analysis that we can get by using item response theory techniques instead of Stone Age test technology. So now you have an idea of what rash models and item response theory are about. They're efforts to get beyond the problem of the nexus so that we can develop a more sophisticated model of our measures and our constructs without having to go through the clumsy, put all the variance on one side, then put it all on the other. In many cases, you'll find that current item response theory interpretations of measures aren't that much more accurate than the Stone Age models, but in some cases, they're actually a substantial improvement. For example, in the days of the WAIS-R and the WAIS-3, I routinely allocated 90 minutes for an IQ test because it legitimately took 75 to 90 minutes to do all 10 or 11 subtests. But with the WAIS-4, it reliably takes 45 minutes to get a good IQ. That's because the people developing the test moved to item response theory when developing the subtests. So now they have a much finer tuned ability to estimate where you are on a scale of ability on each subtest. And much more often, I see people get 8 items correct and then miss 3 in a row. Whereas in the old days, it was considerably more common to get 5, miss 2, get 3, miss 1, get 1, miss 2. So the tests are more consolidated, and the result is I can get to just as good an estimate in literally half the time. So when staying up to date with research methods, rash models, item response theory, that will be something to review and keep up to date on periodically as your career develops. And the last topic, have you ever wondered just who Bayes was and how he turned into an adjective? Well, all of the statistics you're familiar with, going back to Fermat and Pascal and forward to Fisher, all of those start from assumptions about the shape of reality. They're based on, for example, coins or dice, and based on the known behavior of certain objects behaving randomly. These people developed formulas and equations which they could then apply to real-world observations to analyze variance. Bayes started off with knowing nothing about the shape of reality. He doesn't start by assuming that the coins are fair or unfair or that they're evenly distributed. He doesn't start with coins at all. All we have is our observations. And his question was, what can we deduce about nature given just our observations? There are several differences between the Bayesian and the frequentist statistics, Probably the most important is that Bayesian methods allow us to update old knowledge with new observations. In the frequentist world, each experiment is a reboot, and then you have to do an after-the-fact meta-analysis to combine findings. But with Bayes, you can start with an estimate from an earlier experiment and tweak it based on new observations. So let's say that we make mosquito nets to protect people from malaria. They're coated with a chemical that eventually wears off in the tropical heat, and once it wears off, mosquitoes can get through the net. We want to give our customers advice as to how long to use their net. So we test 3 nets. We set them up with detectors inside to pick up on the first mosquito coming in. The first net, a mosquito comes in after 10 days, the second after 12 days, the third after 15 days. And our question is, what's the confidence interval for when the chemical fails? Well, if you're in a frequentist world, the best we can do is take our 3 observations, calculate a standard deviation, and then go plus or minus 2 standard deviations from the average. And we get a confidence interval from 10.2 to 12.2. But we can think logically about these observations. As long as the chemical is active, the mosquitoes can't get in. So we can tell from our 3 observations that by the 10th day, the chemical can break down. So 10 days is the maximum, and you'll notice the frequentist confidence interval is all above the 10-day line, at which point at least 1 net had already failed. So if we start with an assumption that our chemical lasts 10 days, and then we analyze those 3 numbers using a Bayesian method, we come up with a 95% confidence interval for earliest breakdown of 9 to 10 days, because it can't be more than 10. So now we can advise our customers, use your net for 9 days and then get a new net. Now, neither Bayesian nor frequentist statistics are right or wrong. They make sense in different domains. Frequentist statistics make more sense when you know something about how nature is working so that you can select a distribution that models nature well. Bayesian statistics make more sense when you already have some knowledge, like that 10-day breakdown, and you want to fine-tune that estimate, or in conditions where you have no knowledge at all and you want to know how much your current observations can tell you. In simple cases, frequentist and Bayesian will usually give you the same answer, but as conditions become more complex, they diverge farther and farther, and there's a place for each. So if you think about a confidence interval, what does it tell you? Well, we tell people that if you have an IQ of 98, there's a 95% confidence interval that your true score falls between X and Y. That is incorrect. That's a Bayesian interpretation of a frequentist statistic. Our confidence intervals come from Gauss, and what they say is that if you score 98, and we renormed the WAIS-4 1,000 times, 95% of the time, the confidence interval we generate for your pattern of responses would contain your obtained scores. Now, that isn't naturally how we think. I noticed that the Bayesian interpretation matches how we actually think better. So, like with item response theory, Bayesian statistics is something to get familiar with, not from the standpoint of a user, but from the standpoint of a reader. And there are YouTube videos out there that you can gradually tap into to start building some intuition about how the Bayesian side of statistics works, because it's becoming more and more popular. Thanks for your time and attention, and good luck in your future career.